Part 3 of our vector series here, and we're finally ready to multiply two vectors together. You probably noticed that we added two vectors together and we subtracted two vectors and we multiplied a vector by a scalar just by distributing, but how would we multiply two vectors together? Well, it's not called scalar multiplication anymore, it's called a dot product. Okay, a dot product, what I'm going to do is I'm going to take two vectors, A, B, and C, D, and it's really weird how this is going to work, but what I'm going to do is I'm going to take the first two components, I'm going to multiply them together, and then I'm going to take the second components of each vector, B and D, I'm going to multiply them together, and whatever that gives me, I'm just going to add them up. And that is a dot product of two vectors. Well, why would I ever want to multiply two vectors together? Well, you might be wanting to find the angle between them. Okay? And so to find the, let's add a word in here real quick, to find the acute, I don't want to throw that word in there. Never mind. I'm thinking something different. I'll have to hold that thought. I want to find the angle between two vectors. I can use this formula. I'm going to modify it just a little bit to where cosine theta is equal to v dot u over magnitude of v magnitude of u. Okay? So I'm going to rewrite it just a little bit so that we don't have to worry about multiplying here at the end. I'm actually just going to dot the top together and then divide by the scalar that I get on the bottom. Let's put this to work. My goal is to make this so it's the shortest video of the week, so wish me luck. Here we go. So I want to find a dot product, just a straight dot product between these two vectors. So I'm wanting to do v dot u. Okay? So v dot u is going to be, well, I'm going to take my first two components right here, and I'm going to multiply them together. I'm going to add that to my second components, 12 and 4 multiplied together. As you can see, that's not, it's not just straight intuitive like a lot of our other stuff. We're going to need some practice with this in order for this to stick. And so this gives me negative 15 plus 48. And so it's really weird. When I take the dot product of two vectors, the answer is just going to be a number, or as they like to call it in vectors and in physics, a scalar. Okay? Your answer is not going to be a vector. I have a lot of people tell me that this is going to be the answer as a vector, but it's not. Okay? The answer is just going to be 35. So part B, let's try to find the angle between them. Okay, find the angle between these. All right, so I've got my dot product still. So I've got cosine of theta, and again, it's going to be v dot u. I'm going to rewrite it so I remember it. Oops, too many lines. Okay. Well, I just found v dot u. So if they change my numbers on me, that's fine. But I just found that to be 35. Got a little bit of work to do on the bottom. This magnitude is not going away. So I need to multiply this by the square root of a squared plus b squared. But whenever I do this, I'm just going to work it for v. And so a squared plus b squared, it feels like I did that yesterday, but I'll go ahead and write it out. 5 squared plus 12 squared. And then that's going to be times the magnitude of u. Well, that's just going to be the square root of negative 3 squared plus 4 squared. Got some cleaning up to do here. I got 35 over, let's see, 5 squared plus 12 squared, 25 plus 144, 169. The square root of 169 comes out to be exactly 13. Here I have a 3, 4, 5 triangle. 9 plus 16 is 25. The square root just came out to be 5. Now just get old 13 times 5, which is 65. Now that's not my angle. I'm looking for the angle between them. That doesn't make any sense. But remember, that's what cosine theta is equal to. Cosine theta is equal to 35 over 65, or whatever that reduces to. What does that be, 7/13 or something? Doesn't matter, because I'm going to have to put this in my calculator, whether it's 7/13 or 35 over 65. And so I'm looking for an angle. So cosine is going to switch sides here, and it's going to become cosine inverse. I'm able to get my angle now. I don't even know what that is. So second cosine inverse of 35 divided by 65, 57.4 degrees would be the angle between these two vectors. If I was to graph them out and do all that, which we're not interested in as of yet. All right, you're on your own for part C. I want you to do all this again. I'm going to give this vector to you as a linear combination and see if you can figure it out. Okay, so hit pause on the video and you give it a go. I think I was being nice to you and not giving you any negatives. I don't know. I got my dot product to be 29. Isn't this weird that my angle came out to be 45 degrees? So I tried to preserve everything. I took 29 times 58. I got 1,682, and I typed exactly this in the calculator. I took cosine inverse of this fraction. So I thought if we took cosine inverse of like the square root of 2 over 2, it gave me 45 degrees. I agree. Watch this. This is really cool. Okay. Remember, 29 divided by the square root of 29. Remember, this is just the square root of 29 squared, isn't it? So I can cancel this with one of these. And I'm left with the square root of 29 over the square root of 58. So the square root of 58 is just 2 times 29. So I could break apart that square root of 58 as square root of 2, square root of 29. Look what cancels. I'm left with 1 over square root of 2, which rationalizes to square root of 2 over 2. Lo and behold, if I take cosine inverse of the square root of 2 over 2, yes indeed, it gives me 45 degrees. I say all that to let you know, you don't have to worry about simplifying it. I can get the 45 degrees this way, or if I do simplify it, sometimes good things happen and I can double check myself. Okay? Finally, I kind of like this problem. Got this one from the book. It says, I'm going to draw a picture for this. I have an airplane that's flying at an airspeed of 200 miles per hour on a southeast bearing. Okay, so I know you guys probably haven't talked about bearings very much, but if I have a grid going right here, and this is due north, if it's flying southeast, that means it is coming down this way, right? Meaning that if I am talking about a bearing, just a true bearing, then it has to come off of this straight north line right here. Okay? And I made that vector kind of long because remember, the vectors can represent a lot of stuff. It can represent the speed of the plane. And so the speed of this plane could be, or it is 200 degrees. Oh my word, 200 miles per hour. It's been a long day. Now, there is a north wind. Now, when we talk about north winds, that's whenever it gets colder. So the wind is blowing from the north to the south, and it's blowing, see, from the north to the south right here. I'm going to have everything come from the origin at 16.2 miles per hour. So if I combine both of these, if I combine the fact that the plane is trying to go 200 miles per hour at a bearing of 140 degrees, and there's a south breeze blowing, what happens is I get something called tail to tip, where I get a resultant vector, and I get the actual, it's called the ground speed of the plane would follow along, ooh, is that even straight? Let me try that again. Let's get rid of this guy. It bounced back. Getting out of practice. Oh my goodness. I'm going to pause the video, draw a green line. I'll be right back. That's as good as we're going to get right here. I'm sorry. Okay. So I'm going to rewrite this 16.2 so it's over here. Right? The other one's one's going to stay there, but you can deal with it. Airplane is flying at this speed. I want to know what the ground speed is. So the fact that the plane is trying to come along this blue line right here. The shadow keeps getting in the way. You can't see my shadow, but it's there. And then there's a little bit of a north breeze blowing the plane down this way. It's resulting in the plane following this green line, which I'm not going to try to draw again. You see my efforts over here on my green lines, all right? And so what my goal is to figure out, well, how fast is this plane actually going? Which would be the length of that line. And what is the bearing of the plane? It's trying to go 140 degrees, but it's actually going a little bit further south than what it's intending. Before we get going with this problem, I need a little bit more information, because all I know are two sides of the triangle. In order to solve a triangle, I know I need at least 3 pieces of information. So I'm gonna dig back into my geometry days, and I'm going to extend this wind line coming down so that I get a couple of parallel lines. I do believe that's the mark for parallel lines. And so if these are two parallel lines and they're cut by this blue line that represents a transversal right here, I do believe that this 140 degree angle could also be transposed right here into this angle to give me 140 degrees, thanks to the alternate interior angles theorem. I do believe that's it. And so, so that happened. Now, I know that this side is 200. I know that the angle, or I know that this side is 16.2. And I know the angle between them is 140. Only if we had some way to solve a triangle that isn't right, that had these numbers. So it goes side, angle, side. Wait a minute, that's what we did last week. Law of sines, law of cosines. We're solving an oblique triangle. Now, I'm not given an angle and a side across from it. So I'm going to have to do law of cosines first. And the good news is, if I do law of cosines, I can solve directly for this x right here. Okay, so I'm digging in my back pocket here. You see x squared equals, let's see, that would be the two speeds I'm giving. That would be my airplane speed squared plus my wind speed squared, minus 2 times 200 times 16.2, and then cosine of the angle between them, which I had to get from alternate interior angles. Wow. Okay. So I'm going to do this in pieces. Again, I am a scaredy cat, so I'm going to do this much right here. So I got 200 squared plus 16.2 squared, and that gives me 40262.44. I'm going to end up decimaling everything out anyway, so for today, I'm just going to go ahead and just put all of this in. So cosine of 140, okay, times 16.2 times, oops, I hit minus, times 200 times, I'm going to go include the negative on that. And it gave me a positive 4,963 point, well, let's just call it 64 then. Oh, wait, we're going to go 2 decimal places. 97. I have to take that answer and add it to 40262.44. I get 45,226. Trying to be like 0.41, I guess. Now that is way too fast for an airplane, and I almost forgot, but keep in mind, that's what x is equal to. x squared. I'm wanting the square root of both sides. I'm not going to spend another step on that. So if I take the second square root of the answer I just got, I get roughly about 212.7. And this would be miles per hour. So the plane, it's only registering going 200 miles an hour. Keep in mind, it doesn't have wheels up here in the air, a mile or however far it is in the air. So it thinks it's going 200 miles per hour, but with this wind behind it pushing it at 16.2 miles an hour, it's actually going faster along this green line at 212.7 miles per hour. This is all stuff that pilots have to take into consideration on a windy day before they go flying. All right, now, that's good. Don't stop there, though. I've got the ground speed. It also wants to know the bearing. Now, remember, the bearing is going to be this green angle coming all the way around to the green line. So it's going to be a little bit more than 140, but I don't know how much more. Well, if I can just get my hands on this small angle inside, I should be good. Now, I could go through and do a whole law of cosines again, but that would be pretty tough. Because look, I know that this angle up here, I'm going to call it, let's just call it theta. I know that angle theta right there is across from the side that is 16.2. And from what I just found, I know that this x right here is across from a 140 degree angle. What was that? 212.7. And so my sine theta is going to be equal to 16.2 sine of 140 degrees over 212.7. Okay? And if I just take sine inverse of both sides, I should get my angle right here. 16.2 times sine of 140. Divide that by 212.7. Second sine inverse. And that gave me 2.8 degrees. Now keep in mind, that's this small angle right here. This small angle is 2.8 degrees. So all in all, this airplane, it was trying to go 140, but then it pushed it 2.8 more degrees down right there. And so my bearing is going to be the 140 degrees it was trying to go, plus that 2.8 degrees. So it's actually flying at a bearing of 142.8 degrees. Fun problem. A lot of stuff going on there. You're playing with the vectors. You're doing stuff from last week. It's a great problem that kind of is cumulative of everything we've done over the last couple of weeks. I didn't assign many of these. Okay, I don't think you'll need too much practice with it if you're doing these on your own. But I would say on 33 and 35, I couldn't find any in the homework where you're practicing finding the angle between vectors. So I would go ahead and practice that as well, and we can talk about the answers that you get later this week.